This lecture we're going to introduce multiple period inventory models, or we call it inventory replenishment models. Before we talk about the model setting up and the solutions and the performance measures, we first actually use this video to prepare you with the demand forecast and the demand models. So we start with an example. So here we're talking about a supply chain. The supply chain consists of one single distribution center and 500 sales territories. Basically, this is a distribution-centered networks. So they have multiple retailers. The sales territories has sales representatives. They actually directly sell the product to the doctors in the surgery. So, for example, we consider an example of sales territories called Susan's territory, and then the objective is to actually make the inventory decisions about the order quantities or the order replenishment policies in the distribution centers and in each individual sales territories. So in this problem, we can see because the gross margin is really high and develop a system to minimize the inventory investment while maintaining a very high service target. So here the service target is a 99.9% in-stock probability. So that's basically the decision objective. So we continue to look into the inventory problem. So first, we can use the graph or this figure on the right corner. You can see this is example with L equals to 1. So we look into a multiple period problem because this pacemaker is a durable product. So they can sell this product in the long selling season. So when the sales representatives need more stock, they just order more products from the distribution center. So this actually problem allows multiple inventory replenishments. So now if we can see on the timeline, the process is divided into multiple periods. For example, period 1, 2, and 3 actually can continue. And in each period, the distribution center and sales territory needs to actually make a decision about the order. So how many units they should order in each period. And in each period, they will also receive the orders from previous period. So in this problem, in this example, we assume the lead time is 1 period. So in each period, you will just get the order from the last period. And then there are also the outflow of the products, which are the demand occurs. So there are inflow and outflow. So this is the inventory replenishment process. So here let's see the timing in the order up to model. So we call this type of model described in this figure actually is called the order up to model. So in each period, the decision is how many units to order, and then they order up to a level, for example, capital S. So time is divided into periods of equal length. For example, this period can be 1 day, or 1 week, or 1 hour. During a period that following sequences of events occurs, we have mentioned, so a replenishment order can be submitted. And then for the territory, they submit the order to the DC. So in DC, they submit the order to the suppliers. Inventory is received in each period from the previous periods. And the random demand occurs. So here the stochastic factor is the consumer demand. And then the lead time is received after, so an order is received after a fixed number of periods. This is called the lead time. So in this figure, we assume the lead time is 1, but actually the lead time can be 1, 2, 3 or more periods. And then we let the L represent the length of the lead time. So here we quickly compare the news window model and order up to model to help you to understand the difference between the multiple period models and the single period models. So first, the news window model is a single period model. After one selling period, then the inventory be obsoleted. And the order up to model actually allows the product to be sold in a longer selling period or multiple period. And the news window model allows only one single replenishment. But of course, it's possible to have an emergency replenishment during the selling season, but it's actually considered as a short selling season and a limited number of replenishments. And the order up to model has an unlimited order numbers. So whenever you need more products, just place an order. And the news window model actually no demand actually occurs during the replenishment. So that means before the selling season starts, there is no demand. And the order up to model, during the lead time or during the time you wait for your products, you always have the continuous demands increase. And then the news window applies to short life cycle products with uncertain demand, and the order up to model applies to long life cycle products with uncertainty but stable demand. So given the Medtronic's supply chain inventory replenishment problem, we actually first talk about the how to choose a demand distribution or forecast for your problem. So before we see the inventory models, let's first see the demand and the inventory at the distribution center. So average monthly demand in the distribution center is 349 units, and the standard deviation of the monthly demand is 122.4. This can be easily estimated if you have a historical sales data. So in the figure on the right hand side, you can see the demand information and the inventory information for this distribution center. So the these red bars are the actually demand in each month. This quite actually fluctuates. And the blue lines, so these are the inventory at the end of each month. And now we can see this demand information from the previous 1 year, can see from January to December. So it's easy. You need to find historical data for this product, historical sales data, and also you need a historic inventory data. So given the demand actually fluctuates a lot from month to month, you can also see the inventory position or inventory levels also actually fluctuate a lot. So how actually the purpose for inventory control is to actually minimize the inventory levels, average inventory levels, at the same time actually guarantee a high service levels. So in this example, we can easily see, or it's actually a common sense to consider the demand as a normal distribution with a mean and a standard deviation. So this is the demand information and the inventory information from the previous year in Susan's territory. So for example, this is an example of individual territory. So the total demand for the entire year in Susan's territory is 75. So we have a total annual demand of 75 units. And then it equals to our average daily demand 0.29 units. And then assume 5 days per week. In 1 year you have 260 days, and then you have a total 75 units. That's how you work out the average daily demand. So this average daily demand is very small, even less than 1 unit. So the Poisson demand distribution works better for slow-moving items. So in that sense, we decided to model the Susan's territory's inventory problem based on a Poisson model. So after we talk about the Poisson distribution for Susan's territory demand, so the demand is we talk about the demand should be modeled as a Poisson distribution in Susan's territory, and then let's first see what is a Poisson distribution. So the outcome, a random variable with a Poisson distribution, is discrete and positive. So that's a features or characteristics of a Poisson distribution. The Poisson is characterized by a single parameter. So the Poisson distribution actually is characterized by a single parameter called mean. If we want to interpret this value, then we can interpret this as a customer arrival rate. Within arrival rate in unit time. The standard deviation of a Poisson distribution is equal to the square root of its mean. So Poisson distribution actually has a standard deviation, but we actually not really use that to model the demand. So Poisson is related to the exponential distribution. So if you talk about the inter-arrival times between the consecutive customers, then the inter-arrival time normally is exponentially distributed. So the Poisson is ideal for describing the demand of slow-moving activities. Normally we see if the average sales is 20 or fewer. So if your demand is less than or equals to 20, then it's suggested to use a Poisson distribution. So the Poisson's density function takes on different shapes depending on its mean. With a large mean, typically more than 10, the Poisson takes on a bell shape. Is on the right-hand side figure. You can see if the mean is 5, 10, or 20, then basically close to or similar with the bell shape distributions. For example, normal. And then in the left-hand figure, you can see when the average or the mean very small, and then smaller than 5. So the Poisson takes on different shapes. It looks quite different. Also, you can see there is a high probability the occurrence of your demand will be a 0. So it's actually relatively high probability for demand equals to 0. So if you observe your historical sales, you found a lot of zeros. So that's actually a sign to consider the demand as a Poisson distribution. As we have done in the Nussweiler model, if we assume the demand is a probability distribution, then we actually use the distribution properties to find the optimal order quantities or to find the stock in stock or stock out probabilities. That's similar for the Poisson distributed demand models. We can actually take advantage of Poisson distributions properties. We can do further analytical analysis for your problem. First, in Excel, we have actually a Excel function for Poisson distribution, which is a Poisson dot distribution with your value and mean. So you should give a mean and you get a zeta or s value. So this can be directly found. So this is a probability of the demand equals to or less than s. This from the normal distribution. However, there is no inverse Poisson distribution. That means we cannot directly find the order quantities if you have a targeted service levels. In that sense, we actually need to use a Poisson's distribution table or the loss function table. So here we have a part of the table presented on this slide. Now you can see if your order quantity Q is a value, takes the value 0, 1, 2, the different values in the first column, and then you can easily find the probabilities of density probabilities small fq. So this is actually density function. And then we have fq, capital Fq. This is our accumulated probability distribution. And then furthermore, we have a loss function calculated in this table. So the loss function Q is calculated for different order quantities. In order to find the loss function values given different order quantities, then you have to use this table. For the small f and the capital F values, you can always use Excel. So we probably need to plus accumulate or non-accumulate. You can use Excel function. So here is a small exercise for you to to try to find the distribution probabilities from Poisson distribution, or the loss function values. You can take some time to do the exercise yourself first. So if you have tried to work on this exercise, then you can see the solutions in next slide. So the first question is what is the probability that the demand is exactly 2? So in other words, now if Q equals to 2, and then I will say D equals 2, and then if we consider to use the table in the previous slides, this actually should use a solution f small fq, so it's actually equals to the same value. And of course you can also use the Excel function, then you find the same value. And then this next question, what is the probability that the demand is no more than 3? So here we actually see the demand less than or equals to 3, and then you can use the cumulative Poisson distribution function. You find this value, and this can also be actually calculated by directly read the value from the Poisson distribution table FQ. So it's Q equals to 3. So that's how you find the same value. So next question, if you have 2 units to sell, then what is expected lost sales? So that's actually need you to read the result from LQ, the column of the table LQ. So you need to find the column LQ. Now the Q equals to 2, and then the lost sales, expected lost sales will be 0.8011. So this actually how you use the Poisson distribution table, including density functions, distribution functions, and loss function. So here the difference is about the new result about the loss functions. So this actually is particularly important in the inventory management. So in different situations, we need to work out the loss function, leftover inventory function, and so on. So this is about the Poisson distribution and how to actually use the Poisson distribution to find the order quantity or the probability of the order quantity or the loss functions for the certain order quantities. You should actually prepare this before next lecture on Monday.